All right, so today we're going to continue our discussion on regression lines. So we discussed kind of the basics yesterday with given an equation, how do we predict? And that was kind of the whole purpose of these regression lines, is to predict values of y based on values of x. We talked about residuals. So when we actually do make those predictions, how far off are we at a given point? We talked about extrapolation. So when we use our model for predictions, we want to make sure we stay within the scope of our data. Once we leave that scope, we're not sure what happens to the association, and so we can't necessarily guarantee the accuracy of any predictions we make outside of it. So for today, like I said, we're just going to kind of further that discussion with this regression analysis is what we call it. And so the first thing we're going to talk about is how to calculate the regression line. So yesterday, one of the things we mentioned was our general form for our regression line. That was that y hat is equal to a plus bx. So the y is the value that goes with the response variable. The x is the value that goes with the explanatory variable. We talked about the symbol. So that caret symbol on top there means that this is a predicted value of y. So when we use this equation, we're not giving actual values of y, we're giving what the model predicts the value should be. And then we talked about within that equation, the a value represents the y-intercept of our equation. The b value represents our slope. And so one of the first things we're going to discuss is when we calculate the regression line, we're going to use two formulas, one to calculate slope and one to calculate the y-intercept. Now when we go through this process, slope has to be the first thing we calculate. And when we look at that formula, this is a formula you will not have to memorize. So this will be given to you in the formula package when you take those tests. So they'll give you that y hat equals a plus bx. They'll give you the formula to calculate b. They'll give you the formula to calculate a. So you do not need to memorize these. You simply need to know how to use them. And so as I look at that slope formula, it brings back some of the things we've discussed back in Unit 1 and in this current unit as well. So for instance, what does that R represent here? So R would represent the correlation. So that's something we're going to need to calculate. Or in a lot of questions where they ask you to use the formula, they might give that to you directly. So I need to know the correlation between the two variables in question. What does that SY stand for? Standard deviation, specifically for the response variable. So knowing which variable is explanatory and which variable is response is going to be very important in this process. It's always the y variable over the x. So the response over the explanatory. So S sub y is that standard deviation of y. S sub x is standard deviation for x, our explanatory variable. Okay, so I need to either calculate or be given those values. And when I'm given those or I find those from the calculator, I plug them in according to the formula here. So correlation times the standard deviation of y divided by the standard deviation of x. So that's the first formula. For the second formula, we're using an idea here where the regression line passes through what's called the mean point. So when I create this line, we have our y-intercept as our starting point. We get a slope that takes us through hopefully the middle of the data. And what happens is when we create that regression line, it passes through the point x bar, y bar. Every time. So every regression model we calculate passes through the point x bar, y bar. So passes through the exact point where the mean for x and the mean for y meet. So because of that, we can use that point with the slope we calculated in that first step to then convert and calculate into the y-intercept. So if I'm looking at my original equation, I'm replacing the y hat with y bar. I'm replacing x with x bar. I already calculated slope. So the only thing I'd be missing in my equation is a. So if I subtract the bx over to the other side, I'm able to solve for a and get that y-intercept, that starting point for my regression line. And so again, when we're looking at these and they ask you to calculate by hand, they're either going to give you the information to plug in, or you're going to be able to calculate it using the calculator, and we'll talk about that in a little bit here, but that's going to be kind of what we're looking for in terms of creating the regression line. So then once I have my slope, I plug that in for B. Once I have my y-intercept, plug it in for A, and I get my regression line. Okay. So if we think back to our example from yesterday with the Burger King example. So they were taking menu items. They measured the amount of protein and the amount of fat in each item. They used the amount of protein as their explanatory, the amount of fat as their response. And so if you are given the summary statistics for the amount of protein and the amount of fat, so that's what's happening over on the left side here. So they're giving me the mean and standard deviation for the amount of protein. They're giving me the mean and standard deviation for the amount of fat. And they gave us the correlation between the two values as well. So they just basically gave us the pieces we need. We just need to know how to put them all together. So as I'm looking at the formulas there, okay, the first thing they started off with was taking the correlation. And plugging it in for R. We take the standard deviation of Y, plug it in for S sub Y, standard deviation of X, plug it in for S of X. So we just put the three values in, we plug that in our calculator, and when we multiply and divide that all out, we get that 0.97 like we had yesterday for that slope. Once we have that slope, then we can take that and use it to plug in and find our y-intercept. So we take the mean for y, we take the slope that we just calculated, and we take the mean for x, and we plug those into the second formula, and we calculate that y-intercept, that 6.82 like we had yesterday. Once I have my two values, the next thing I do is I plug them into the formula, or plug them into my equation. Now notice, we said our general form is that y hat is equal to a plus bx. Yesterday, every equation we got was in that same form, a plus bx. Now in this case, we're still in that same general form, but I do want you to be aware that in certain cases, they might flip-flop that slope and the y-intercept in terms of like the order in the problem. So if they put the slope first with the x and the y-intercept second, it's the same thing. So I just want you to be aware that you can see it either way. Okay, it's still a for y-intercept, it's still b for slope. And then like we talked about yesterday, if I use the y hat and the x, I then need to accompany that equation with y equals the amount of fat, x equals the amount of protein to define the variables. Otherwise, I could use the second option here where I plug the values of the variable in. So the predicted amount of fat is equal to 0.97 times the amount of protein plus 6.82. So the way you write the equation is up to you. But every time we write it with y and x, we have to define y and x. Otherwise, if I put the variable names in, I'm good to go with that. And so that's the basic idea there. Now in the homework, when they give you these types of problems, they ask you to create the regression line by using the formula. They're going to give you the information like we did here, but they're not going to specify x and y with each of the different values. They're going to tell you for this variable, the mean and standard deviation are this. For this variable, the mean and standard deviation are this. You have to make the determination on what's the explanatory and what's the response. So in this one, we had already discussed that previously. In the homework, you're going to have to figure that out. Now, the way you do that is by looking at how they word or how they phrase a regression equation. So if this were the problem that they were talking about and they did not give me the x's and y's, so if they just said, I'm going to look at the amount of protein, I'm looking at the amount of fat, the way they're going to say that is create a regression line that allows us to predict the amount of fat based on the amount of protein. So by phrasing it that way, they are telling you which they want to be the explanatory and which they want to be the response. Since they're saying we want to predict the amount of fat, that becomes our y automatically. We're always predicting y. And we're doing it based on the value of x, which is going to be my explanatory variable. So listen or pay attention to the wording as you read through those questions. They're going to tell you which should be which. And then placing the values in the appropriate place, plugging the calculator and finding your answer. Everyone okay with that? Okay? So you're going to get a couple problems like that on the homework. Next thing then, so back to, we talked about this example before when we calculated correlation. So stats teacher wants to see if there's a strong association between the number of days a student misses and the student's semester grade. He collected data for 5 of his students. It's given in the table below. Now this says find the least squares regression line by using the formula. We've already done that, so we're going to go ahead and do the calculator version right now. But I do want to at least talk you through what this would look like if I did want you to do this by hand. Okay? So in the previous problem, I gave you x bar and sx, I gave you y bar sy, and I gave you r. If this were the type of problem that they wanted you to create using the formula though, you would have to find those 5 values yourself. So if that were the case, when I look at my 2 variables, I have to determine explanatory and response. And so we already kind of discussed this, which one was my explanatory in this case? The number of days absent, that's my x variable, and then the semester grade was my y. That means the number of days absent goes in list 1, the semester grade goes in list 2. So what I want you to do is in your calculators, go ahead and put these in. This is the first step in creating the regression line on the calculator as well. And for that matter, almost anything we do on the calculator, the first thing we have to do is put everything into the lists. So get those entered. Some of you might have those still in there from last week if the calculator got used for this example. Just double check that the numbers are correct and paired correctly. So once I have my 2 lists, okay, if I were wanting you to do this by hand, so if I were to actually want you to do this using the formulas, once I put the values in, I need to calculate all 5 of those values I need for the formulas. So I need the mean for x and standard deviation, I need the mean and standard deviation for y, and I need the correlation. Now I can get those first 4 all at once. So in the calculator, when I have my 2 lists entered, if I go into my stat menu, go over to the calculate tab, and now before, when I wanted mean and standard deviation, we used that 1 var stats because we were only working with 1 variable. Now we have 2 variables in play, so if I choose the 2 var stats instead, so under that calculate tab, if you choose the 2 var stats, make sure you have list 1 and list 2 in your correct lists. And when you enter, so go ahead and calculate all the way through, it gives you a bunch of numbers. So what we're looking for, you should be able to find x bar and sx right on that first screen there. So you would copy those down, whatever they happen to be. We're not going to do it right now. Then I would scroll down, and as I scroll down through that list, I should be able to find y bar and sy right below that. So I would copy those values down. And then the only thing I would be missing to calculate the correlation or to calculate the regression line by the formula would be the correlation. So we talked about that last week. If I want to calculate the correlation, how do we do that? So after I have my lists in for list 1 and list 2, if I want to calculate the correlation in the calculator, what do I do? We go into stat, go to calc, and then linreg, right? Now, there were 2 options for linreg, and so I want to talk about that real quick here. So option 4, linreg ax plus b. And option 8 is linreg A plus BX. Now, when we calculated correlation last week, we said it doesn't matter which one we choose. Choose option 4, choose option 8, it's going to give you correlation either way. So that's how I would get the correlation to complete the information I need here. Everybody with me on that? Once I have that, then I would go into my formulas to calculate slope, take that correlation that I found, times the standard deviation of y divided by the standard deviation of x, and I'd start going through that process. Is everybody okay with that? So when I say by hand, all of this can be done in the calculator. The only by hand you have to do is the two formulas for B and A. Okay? Now, for this week, we actually want to get the regression line. So it's not just correlation that we're interested in there. We want the actual regression line this time. So you can still choose either option. You can still choose option 4 or option 8, but if you want to keep things consistent with how we are going to notate everything, we are always going to use A plus BX. So in your calculator, my recommendation would be always use option 8, because then A is always your y-intercept, B is always your slope. It keeps it consistent every time. If you're going back and forth between them, then you have to be thinking about which one is my slope and which one's my y-intercept this time. Because in the other option, option 4, A becomes slope, B becomes y-intercept. And if we start mixing those up, we get the wrong equations. So my suggestion, when I ask you to do this on the calculator, I would use option 8. So A is always your y-intercept, B is always your slope. So run that linreg function. And when you run it, you should get that y equals, or y hat equals A plus BX at the top. And then it gives you the values for A, for B, should have correlation squared and correlation. Now for right now, we're not interested in correlation squared or correlation. We'll talk about those later. We're looking at A and B. So for this particular example, what is the A value given in the calculator? And go to 3 decimal places. So 90.765 is A. What is B to 3 decimal places? Negative 1.9 what? 80. Okay. So B is negative 1.980. So those would be the two pieces I'm interested in right now. So if I'm doing this on the calculator, I run that linreg, I want my slope and y-intercept, and then when I put it together, I have my y hat is equal to 90.765 minus 1.980 times x. So I'm taking the two values from the calculator and placing them into my regression equation. Now, if I wrote it in this form, what would I also have to include right now? Say what? What x and y represent. So y represents the semester grade, x represents the number of days absent, so I'd have to make that as a definition. If I had wanted to, I could have put grade in for y and number of days absent in for x, and then I don't have to define it. That's completely up to you how you want to do that. On the answer key, I'll always have it both ways. Okay, but that's what that's going to look like. Now, before we move on to the next thing, so we calculate the regression equation. If I asked you to interpret slope, a little bit of review from yesterday. So if I said interpret the slope of this regression line. So if I think about the context of what we're looking at, my slope is negative 1.98. What does that actually mean in the context of the problem? Layla?
Like for each additional day that a student misses, their semester grade is expected to decrease by 1.98%.
Very good. So what we said was, in general terms, it was for every additional unit of x, y increases or decreases by whatever amount, right? So in this context, we would say for each additional day that a student misses, or for each additional absence that the student has, their expected grade, and it is important that you say the expected or predicted grade, because that's what we're measuring. Not the actual grade, but what we predict. So for each additional day absent for the student, their expected grade will decrease by 1.98%. So remembering how to interpret that slope. If it's a negative slope, as x increases, y will decrease. If it's a positive association, as x increases, y will increase. So that's still an important concept. You're going to see that in the homework today as well. Okay. So, regression line by hand, regression line on the calculator. Everyone okay with those? And you'll get practice with each of those on the homework today. But those are two of the processes we need to know how to work through. Okay. The third process that we need to be aware of is if they use statistical software packages to run a regression analysis for us. So there's lots of different statistical software packages. There's Minitab, Phantom, lots of different others. And when they run their regression analysis, they all more or less look fairly similar. So this would be a regression output from Minitab. And so when we're looking at this, they give us a lot of information in here. Right now, we're only concerned with part of this output, okay? So for instance, if I'm looking at this regression output, and as you are getting those regression outputs in the homework or on a quiz or test, we do not care about standard error. We do not care about t-scores. We do not care about p-values. All of those are going to be a second semester topic. The other thing that we can completely ignore every time when we get these computer outputs is the R-squared adjusted. So those are things that either right now or we'll always ignore, but we can ignore all of those values right now. What I'm interested in is that first column. And when I set up these different regression outputs, when they give these reports from the different software packages, this part will always be the same. So this part of the output will always be the same. It's always consistent. So that top number is the constant. That's the y-intercept. So that top number for the coefficient is my y-intercept. The bottom number is always going to be attached to the x variable, which is what the slope does. So constant is by itself. That's my y-intercept. Attached to the x is my slope. So from this regression output, I can write my regression line with my y-intercept at 38,257 and my slope 0.16292 times x. So I'm pulling those two pieces of information out and placing them into my regression line. So using the formula, using the calculator, the lin-reg function, or using these computer outputs, you need to be able to generate regression lines from any of those three methods. Now the other two pieces that are on here that I've highlighted, S, and sometimes depending on the output, we'll have S sub E, and I like that notation better because E represents a what? Residual. So lowercase e was a residual, so this is the residual standard deviation. And we'll talk about what that means in a little bit here. The other one you want to be aware of is R squared. That value is going to have meaning as well, and we're going to talk about that in a little bit as well. So primarily, we're interested in setting up our regression line, so that's finding our y-intercept and slope. But then if they ask us to interpret different parts of the regression analysis, we're going to talk about residual standard deviation and R squared as well. So those are the pieces you want to be able to identify. Depending on the output, okay, like I said, the part that I boxed in here, this will never change on any of those different statistical software packages. That part's going to remain consistent. This stuff's going to move around depending on how they organize it. So sometimes it might be above, sometimes it might be below, sometimes off to the side. So you just have to look for it within the problem there. Okay, so you're looking for S for residual standard deviation and correlation squared. Everyone okay with making the regression line? So 3 different methods. We need to be familiar with all of them, okay? The next part, we're going to go back to our residuals. So we talked about residuals yesterday. We want to know how close the line is to predicting the correct values. So we said when we create these residuals, we're calculating our prediction error. So we're calculating how far off the line was at a given point. So what's going to happen here is we're going to talk about creating residual plots. Now, residual plots are very important for us in our regression analysis because up until this point, when we have been looking at scatter plots, when we've been looking at creating these regression models, we've just used the general scatter plot to determine if we were linear or nonlinear. And in most instances, that will work pretty well. But the problem with scatter plots is they can sometimes hide nonlinear patterns. So it may look fairly linear on the surface, but there might be an underlying nonlinear association that we can't see in the scatter plot. And that's where these residual plots come in. These will magnify any nonlinear relationship that may occur within our association. So what they're going to do here, and we're never going to calculate these by hand, this will always be in the calculator, or 99% of the time they're just going to give you the residual plot and ask you to interpret it. But where they're coming from, they're taking all of the x values. So notice the x-axis doesn't change. I'm still using the first variable of my explanatory variable as it was. But instead of looking at x versus y, what we're going to do is we're going to take a value. So if I look at like this value right here. So for that particular point in our data set, they took the x value associated with that point. They plugged it into the regression line. They found the predicted value of y, and they subtracted it from the actual value of y. And that residual that they calculated is what they placed on the y-axis now. So in this case, they got a residual of about negative 0.3. And then they went to another point. They took the associated x value, plugged it in, calculated the predicted value of y, subtracted from the actual value of y, and plotted that residual. So what we're looking at is how far off the line was from each of these points when we predicted. And so we notice with the y-axis it changes. Now we have positive and negative values to account for because sometimes I overestimate, sometimes I underestimate. And so we have to account for both. So that's where these are coming from, just kind of the basics behind it, okay? Now what we're looking for are any patterns. If I see any patterns in my residual plot, then it means that I have a nonlinear association. If I don't see any patterns, if I just see a random scatter, like in this case, I have random scatter around the line all the way from start to finish. There is no pattern, there's no curve, there's no anything in there. If that's what I see, that's what we want. I want to see random scatter because it means my linear model is appropriate. And that's how you're going to interpret these. When they give you the residual plot, they're going to ask, is a linear model appropriate for the data? You look at the residual plot, you notice that it's random scatter, there's no curve, there's no pattern within it. Then you say, yes, the linear model is appropriate because there's no pattern in the residuals. Okay? But if I create my residual plot and I get something like this, now this becomes a problem. So I created my regression line, I fit it to the data set. When I calculated my residual plot, this is what I see. So I can see a clear nonlinear pattern within my residual plot, which means even if we didn't see it in the original scatter plot, this is a nonlinear association. So when I see intervals where I'm consistently overestimating and then consistently underestimating and then consistently overestimating again, so it's not the random scatter. When I see those patterns emerge like this one, we know that we have a nonlinear association. So if they asked for this question, we would say the linear model is not appropriate. It's a nonlinear association because we see that nonlinear form in the residual plot. Okay. The other thing just to be aware of, this does not show up very often, but there is a pattern that can emerge within a residual plot. It's called fanning. Now, when fanning occurs, what you're going to notice is from start to finish, you do have a random scatter of points. But what's happening, like in this instance, I was predicting very accurately for low values of x. But as x increased, my predictions became more sporadic or a little bit further off. Okay, so they were less accurate as x increased. Now, if they ask, is the linear model appropriate? The linear model is still appropriate in this scenario because I do still have random scatter above and below all the way throughout. But we would want to make note of the fact that the prediction accuracies are going to decrease as x increases. So I should be really close when x is low. I'm going to get further away when x is high. So fanning, and it can happen the reverse way as well, where we get more accurate as x increases, but that's a thing that we can identify as well. So basically, what we're saying there, as far as residual plots go, they should basically be a random scatter of points. There should be no discernible pattern. So if I see that random scatter, that's what we want. My linear model is appropriate. We see any sort of curve pattern, we're not appropriate because we have that pattern in the residuals. Now, if I want to create a residual plot, so let's talk about that real quick. Like I said, 99% of the time, they're just going to give those to you, but on your calculators, we can do residual plots. So you already have your data entered into list 1 and list 2. So that would be your first step. Now, the next step is to run your linreg function. And I want you to just rerun it, just so you get the practice with it. But as soon as I enter my data, I have to give my calculator a regression line to work with. So go into stat, go to calculate, run the linreg function again. Now, if I'm going for a residual plot, once I run the linreg, I really don't care about any of the numbers that come up there. I just need to run it so the calculator stores that equation in its memory. Does that make sense? As soon as I change my data, I need to make sure I rerun my linreg to get the new equation stored in the memory. So every time I go to a new problem, I need to make sure I change that linreg. And so once it has the line, it's got it stored for you, we are going to create the residual plot from here. So now we run the linreg. Now we go into second y equals, go into your stat plot menu. Go into plot 1 and make sure it's turned on. Make sure to select the very first graph option, the scatter plot. Now this time, when we look at X list and Y list, has list 1, list 2 like we should have already, right? So then what I want you to do though, is we don't want list 1 and list 2. That's my regular scatter plot. I want to modify it to become a residual plot. So what I'm going to do next is I'm going to highlight list 2. So scroll down to the Y list, so list 2 is highlighted. Go to second stat. And by going to second stat, you end up in a list of your lists. You want the one that says resid for residual. So choose that option. It should be at the bottom. It should take you back into your stat plot menu. So now you should see X list is list 1, Y list is resid. So now if you hit zoom and the number 9, you get your residual plot. And so what I would expect on a problem like this, if you were creating a residual plot, you would take what you see on your screen there and provide a sketch on your paper. And then you would make your interpretation. There is no pattern in the residual, so a linear model is appropriate, or we do see a pattern, so the model is not appropriate, okay? But that's gonna be the process for setting up that residual plot. Now, like I said, each question you go to, you're going to have to re-enter new data into list 1 and list 2. So you need to rerun that linreg function so it gets the new line to associate with the values you have, and then it'll create that residual plot every time. If I want to go back to a regular scatter plot then, so let's talk about that just real quick. If I want a regular scatter plot again, go back into second y equals, go into your stat plot menu, and go back into plot 1. Scroll down to your y list. And if I want to switch back to list 2, I want just my regular scatter plot again, just go ahead and hit second and the number 2. And now you have list 1 and list 2 again. Now if you hit zoom 9, you get back to your regular scatter plot. If I want to go back to a residual plot, then I highlight list 2, I go into my second stat, I choose the resid option, zoom 9, and I get my residual plot. Okay? So that's that process there. Next part then, residual standard deviation. When we create these regression analyses, we get this regression model that's supposed to predict the values of y based on the values of x, and hopefully as accurately as possible. But we said the data is not going to line up in the real world, so we're always going to have some prediction errors. That's what the residuals are. So what residual standard deviation tells us is what the typical prediction error will be when using this model. So when I use my current regression line to predict values of y, my predictions will typically be off by whatever number that residual standard deviation is. So this is exactly like our regular standard deviation as well. Our regular standard deviation was the typical distance from the mean. Well, in this case, our mean is the regression line. So we're talking about the prediction, or the typical prediction error, the typical distance from the line. As far as residual standard deviation is concerned, you will not have to calculate this. This will be something that they'll give you in the problem, and they'll ask you to interpret it. So that's the key thing here. So when using my regression line to predict y, we will typically be off by whatever amount. And we'll look at an example here in a second. The other part of this regression analysis that we need to be aware of, correlation squared, which is called the coefficient of determination. Make sure to get this phrase or this term down in your notes. So they will call it R squared sometimes. They will call it the coefficient of determination others. So you need to be aware of both terms. But correlation squared is exactly what it sounds like it is. It's my correlation coefficient squared. So in the pictures below here, on the left side on this graph, we had a correlation value of 0.994, so very strong positive linear association. My correlation squared value would be that 0.994 squared. We'd literally just plug it in the calculator. So when I take 0.994 squared, I get 0.99 or 0.9880. Now correlation squared is always going to be reported as a percentage. And when we interpret it as a percentage, so 98.8%. Or for the one on the right, correlation value of 0.932, square the 0.932, we get 0.8686. So our correlation squared would be about 86.9%. What the coefficient of determination tells us, what this correlation squared value is the percent of variation in y that's accounted for by the model. So there's variability happening for each x value from y value to y value. The line is trying to capture the majority of that variation. So R squared is the percent of variation accounted for by the model. It's always a number between 0 and 100%. And then the thing it really measures for us is how accurate the line is. The higher my percentage for correlation squared, the better fit the line is, the more accurate my predictions are. Now, just like with correlation, correlation squared should only be used in linear associations. Just like our regression line should only be used in linear associations, so we do need to verify that that's the case. But this is something where they'll pretty much usually give it to you and you're just interpreting. What does that percentage mean? Now, the thing I want you to be aware of, if they want you to use correlation or correlation squared to calculate the other, if I start with correlation, getting to correlation squared is simple. Take the number I have, square it, I get my correlation squared. Even if my correlation is negative, when I square it, it's going to become positive, which we then convert into a percentage. But that's the thing that we have to consider when we're coming back the other way. If I have the correlation squared value, so on a regression output, they're going to give you the correlation squared value. If they want you to convert that back to a correlation coefficient, they want you to find R. The first part is pretty straightforward. I'm going to take the square root. So whatever my percentage is, I convert it to a decimal, square root the number, and I'm going to get my correlation value. However, I need to make sure that my correlation value matches the direction of my association. So if I have a positive association, when I take the square root of R squared, I take the positive root as my correlation. If I have a negative association, I take the square root of my correlation squared, and I need to make it negative to match the direction of my association. So there's just one more thing to consider. If I have correlation squared and want to go backwards, I need to make sure that my correlation matches the direction of my association. Okay. So then going back to the example from yesterday, we talked about the average number of points scored per game and the number of wins for some SEC teams. Now, what we talked about yesterday were things like interpreting the y-intercept, interpreting the slope. We talked about the residual, right? So those were topics for yesterday. For today, we want to take into account this whole regression analysis. So we've got the regression line. We now have talked about residual standard deviation, correlation squared, and the residual plot. So all of this comes into play when we start going through our regression analysis. So one of the things they might ask us, given a problem like this, it might say, is a linear model appropriate for these data? And explain. So if I'm looking at whether a linear model is appropriate, I'm looking for the residual plot. So this is what I use to make my determination. When I look at that residual plot, if I don't see any pattern, if I just see a random scatter of points, then we have what we want. So in this instance, a linear model would be appropriate for this example because there is no apparent pattern in the residual plot. So I have to have that residual plot. I'm looking for any patterns. If I don't see any, then that's exactly what we want. Okay. When we interpret standard deviation, so for this particular example, so we can see what that looks like, the standard deviation was 1.24. So what that means is when we use our model to predict the number of wins, we will typically be off by about 1.24 wins. So anytime I use this model, if I use it over and over, on average, I will be off by 1.24 wins from the actual number of wins for that team. And then for correlation squared, so correlation squared in this case is 0.88, that means 88%. So when I interpret that, about 88% of the variation in wins, so it's always the percent of variation in Y, is accounted for by the linear model. So anytime they're asking you to interpret correlation squared, it's this percent of variation in Y is accounted for by the linear model relating wins to points in this game, or in this case. All right, last couple of things here. When we're working with these regression analyses, making sure we make the distinction between explanatory and response variables is very important in the overall analysis. Now, when I look at the two examples here, they've taken the explanatory variable and response variable and flipped them. So in the second example here, they took the x and the y, they flipped them around. Now, some things that are the same. When I flip that x and y relationship, I still have a negative association. I still have a linear association. I still have a fairly strong association, or moderately strong, okay? But when I look at the regression values, notice our regression line changes dramatically. So my slope and y-intercept are completely different. My residual standard deviation also changes drastically. So how close I am to the prediction values. Correlation squared doesn't change at all. Now, why is that?
Because you use z-scores to find the correlations with the non-relational.
Well, so the z-scores, so using the z-scores tells us that the units don't matter. But when we calculated it, we said that we take those z-scores and do what with them? From our formula for correlation, what did we do with the z-scores? We multiplied them together, right? And multiplication is commutative. So if I move the x and the y, it doesn't matter. I'm still going to get the same product. So this just illustrates that if I switch x and y, correlation, and therefore correlation squared, remain intact. So it's still the same correlation value, still the same correlation squared value, but everything else dramatically changes. So we want to be aware of that and make sure we have the right determination. The other thing, correlation and regression lines, again, only describe linear associations. So there are 4 different graphs up on the board here. All look drastically different, but they all have the exact same correlation value and the exact same regression line. And this is to show you that we can calculate regression lines, we can calculate correlations for anything, but it's not going to be accurate if it's not a linear association to begin with. So as we're looking at this, the correlation and the regression line are appropriate for this first example. This is a linear positive association. That's fairly strong, backed up by the correlation coefficient. When we look at the second example here, though, the correlation value is 0.816, but this is a nonlinear pattern. So the correlation value makes no sense for that particular scenario, nor does a regression line, because the values won't predict accurately for that nonlinear pattern. When we start looking at these bottom examples, it starts looking at like the outliers. It's going to be a topic for Friday. When I have outliers, right? The majority of my data is perfectly lined up here. This should be a very strong correlation, but because there's one that falls off the beaten path, has a high residual, it weakens that correlation overall. And so we have that same example, but different results here. So we want to be careful that when we're using these things, we're doing so in the appropriate manner. So then here are the problems I want you to try out for this. Tomorrow is